Hello and welcome back. So let's wrap up the 2D sessions by solving this second test problem. And this problem we have already discussed in the introduction. We can look at it in different ways from the physics point of view, from a physical application point of view. Here we are interested in solving del square phi is equal to 0. And we have two circles here in an infinite domain in which the two circles have Dirichlet conditions, phi is equal to 50 and phi is equal to 0, and they have some and they are just placed adjacent to each other at x coordinates of 0 and 2.5. So the y coordinates for these centers are identically 0. So these are just lying on the x axis, and you have these radius defined as well. So in this case, let's think of it as a heat transfer problem, because our objective is to calculate the secondary variable on these, to integrate the secondary variable on these boundaries. So the secondary variable in case of heat transfer or a diffusive heat transfer is just your diffusive heat flux. In case of a mass transfer, it would be mass flux, and so on. So that is what we want to integrate here. And let's see how to do this, and we'll look at the reaction forces approach, which is very simple. In case of Navier-Stokes equations, you would get the secondary variable as a stress on the boundary. So let's do this. And so an analytical solution for this problem exists, and you can find this logarithmic analytical solution in heat transfer textbooks. But I am using a solution from the Greenberg's textbook on advanced engineering mathematics. So in that textbook, this is actually a solved example, and it's solved by using conformal mapping. So you can think of this problem as also concentric circles. So by mapping it to the conformal plane, you rather the complex plane, you get this in form of concentric circles, and you can simply solve it in your radial coordinates, and the solution can be mapped back. And this is possible because you are having this del square phi is equal to 0. It's not always possible for all kinds of PDEs, but in this case it is possible, and you can get the analytical solution. So I have written it down here, and I will be providing this pseudo code. And in this particular case, since we are ending with the 2D session, I will provide the files in Python and Julia, and you could adapt them for your monopole problem or for any other problem. So in case of Python, you will read the .msh file from Gmesh. In case of Julia and MATLAB, you can read it from .m files. So this is the analytical solution, and this so I am highlighting the analytical solution. You can see this is a logarithmic solution, and it's a complicated expression, somewhat large expression, and because this log of ratio, this guy is really bringing about the effects of the distance between the cylinders and the placement of the cylinders. So really this ratio is coming from this expression, which also has x and y coordinates, and these two guys also, A and R, these expressions, which are also again the expressions which are dependent on the placement of the cylinders. This is somewhat of a big expression, but you have an analytical solution, and since you have this solution, you can also integrate and find out the flux on the flux which is leaving the hot cylinder and which is getting received on the cold cylinder. There are no other boundaries, so what is leaving here will be whatever is getting received here. And so maybe you can just use a different system. Like we could say that heat is leaving the hot cylinder, so we'll use minus q here. So I'm not really so let's have a look if the sign convention is correct, but really we are interested in integrating the flux, and we should get we'll compare this with the numerical value. And in the case of numerical solution, we cannot have an infinite domain, so we'll have to truncate the domain, and we'll see as we increase the domain, the solution will also show a more converging effect. So let's understand this from a heat flux point of view. So let's understand what is the heat flux, and let's just revise that. So for our heat balance, just in the pure diffusion case, we just write it in this form, right? So in this case, phi is basically just equal to T, the phi variable which we were solving for, and K is your thermal conductivity. In this case, we are just taking this K as 1, and this is your heat flux. So temperature is a scalar, and so gradient of a scalar is basically a vector. It has two directions. Right, and when you dot it with another vector, which is your grad, so you get a scalar, and so this is your heat which is being transferred through diffusion, which is a scalar. This guy here, minus k del T, is basically your flux, and to calculate the flux, really it depends on, so you could think of flux as flow of your quantity. So in this case your quantity is heat, so you could think of flow of mass also. So similarly, so it's basically your flow of quantity per unit area. So if you have this curved boundary and you're taking this element, you will have to basically, you are calculating flux per area, so you have to basically define that area. So we just take basically a unit normal in the outward direction for this element, which is just a normal perpendicular to this element in the outward direction, and we will just dot our del T, which is basically a vector with this unit normal in the outward direction. You can have k as well if you want. So this will become more accurate, and so this is your flux, and then you integrate this flux over the boundary. So in case of our finite element representation, we know that these are our shape functions. So this is our code for 2D, and we have our shape function library here. And we saw that in case of triangles, these were your shape functions, 1 minus psi minus eta. So these are for your master coordinates, and we use the isomap to convert it to the physical coordinates. And this is your variation in the x and y direction. So these are just piecewise constants in our case for the triangle. So really to calculate dabba t by dabba x, we will just so if we have a triangle, right, so we have these coefficients of the triangle, which are representing the temperature at these nodes, and these nodes basically just scale our n, which is our shape function, and that is how we get the solution. So the solution inside this element is basically t of xy. So it is a smooth varying 2D polynomial inside this triangle, which we get as summation of I going from 1 to 3. In this case it's triangle, so 1 to 3 ni ti. So this is our temperature variation, and in case of the dabba t by dabba x, we would just do something similar. So we'll just use ti into dabba n by dabba x, and we have to represent it again by our isomap function. Okay, so similarly you could calculate dabba t by dabba y as, right, and then you could, so this is your vector, then you get a vector, and then you just dot it with the unit normal, which will also be another vector, and this would give your flux in the element, right? Of course, to be so this will not be your flux actually. This so you also have to multiply by k, right, minus k. So yes, so now this will be a flux in that element, and then you have to basically just add all of these fluxes over the element, and you will get your total flux, which is moving out of your cylinder or moving inside your cylinder. So it's easy to specify nx and ny. So if you have just a vector along the x direction, this will simply be 1 0. Along the y direction, this can be 0 1, or you can compute it for basically for every element. You can just take the center of the circle, and you can just draw a line, and you can just compute this vector. You can dot it, and you can compute the actual flux. But there is an easy way of doing it, and so this is a complicated way of handling the boundary. but an easier way exists, and we can do it by reaction forces, and this is very common for our post processing. So let's understand this. So for this, first we have to write down the weak form, and so this is the equation that we are trying to solve. So we just multiply by our test function. Let's write this again as, right, this is our equation. So we just multiply this by a test function, right, and we integrate. And so let's also draw this geometry here. So this integral is over omega, which is your geometry, and you also have your boundary, which is called as gamma. So when we integrate by parts, we'll just get this expression. So the minus sign will just get cancelled, and so this is the problem which we solve inside the domain, for which we derive our stiffness matrix, and then this is your boundary integral, right? So this is basically just like your flux, right? And this n guy is basically just your shape function on this boundary. So the way to think of this is basically, if this guy was your, so if this was your quad element, this was your boundary, right? So let's say you map this to a quad again, and so this is the psi direction, this is the eta direction, and let's say these 2 points x1 x2 become these points here, x1 x2. So basically the boundary integral, you could just write this n, which is your, so you could have all of these 4 shape functions here, n inside this quad, and you could just put eta equal to 0, and then this would be your boundary function. Okay, so this is again the same test function which is coming from your weak form, but this is just defined on the boundary. So so once you just transfer this to the RHS, so that's what we do, right? When we write our stiffness matrix and force vector, we note that this guy, this integral over the domain, so this is present in your K, and your boundary integral is your linear form, which is going to this force vector, right? So one way of thinking of the flux is that, so if you remember the Dirichlet conditions that we enforced, so we just had some entries here like k11, k12 and 0, 0, 0. So we just modified this matrix by just putting all the stiffness matrix entries as 0, and we just put 1 at the diagonal element. Okay, so and then we inverted this, so this was our stiffness matrix after application of boundary conditions, and let's call this as without the boundary conditions, no imposition of boundary conditions, right? And after imposition of boundary conditions, we have our k into your unknowns vector equal to force vector. So in this case, we have no flux boundaries, so we'll just have Dirichlet condition imposed in the force vector. So just for the first case, if we are imposing the Dirichlet condition here, so we just on the RHS we'll just add the value of our phi, right, our unknown, or in this case let me just call it as phi. Okay, so this we have already done, and so we just inverted this matrix and we got our phi, right? So this was our unknowns vector phi. So in the reaction forces approach, what we do is we take this unknowns vector phi and we multiply it by basically the stiffness matrix without the boundary conditions. So once you do that, you'll just get a vector, right? And this is the vector which is which you can call as the reaction forces. I'll just call it as R here. So these are the reaction forces, and you could think of it as the reverse force exerted by this system to maintain the imposition of this Dirac-Let condition. Okay, so these come out naturally as a just like a force vector, because this is basically just your phi, right? So this is just another system which is your bilinear form multiplying your unknowns vector. So you just get a force vector here on the RHS, and this force vector is also having this n here, right? N into del t. So this, it has exactly this form, and so you are actually getting a direct integral out as nodal values here. You don't have to perform the boundary integral. You directly get these kind of values, and you just take the sum. So let's just do that, and we'll also compare it with the analytical solution. And for this, we'll have to generate the boundary first. The mesh. So let's do that quickly, and then quickly we'll use our 2D solver, which we just developed in the previous section, to do this solution.